Our next lesson, essential question on natural selection in action, is genetic drift. First, you need to understand what genetic drift is, and then we'll talk about how it may happen in nature. So first, we need a good definition for genetic drift, and the definition that we're going to use is that genetic drift is a change in allele frequencies due to small populations and or random sampling. It's not based on fitness. This is based on chance. It could be based 100% on chance. It could be triggered by some sort of natural disaster like an earthquake, a volcanic eruption, a flood. It could also be triggered by a man-made event, something such as a highway separating a population. But no matter how it gets started, it's all basically the same premise. We have a big change in allele frequencies that's really just due to chance. It's not due to fitness at all. So when we look at this population of flowers here, when we look at our original flowers, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 flowers, and out of the 10 flowers, only one of them is white. So that tells us, that indicates that the red allele is definitely dominating over the white one. But by chance, it could be that the next generation ends up with having 3 whites at this point. So as you can see, the white allele, or the little r allele, is becoming more common. Not because of fitness necessarily, just because of chance. If we continue this example forward into a third generation here, by chance we could end up with all red. The challenge here is that this is probably only happening because it's a small population. If we're talking about a population of 10 plants, we can see those gene frequencies shift one way or the other quite rapidly over the course of a couple generations. So now we've gotten to the point where we don't have any of the little white allele at all. Not only do we not have white flowers, but if you look closely at the figure, there's no little r's in there anywhere. So the white allele has completely disappeared. This typically can only happen in small populations. We don't usually see this in large populations unless there's something else going on. And that's what our 2 specific examples are about. What if there's something else going on? Our 2 examples are the founder effect, and then once you get done with that, we'll talk a little bit about the bottleneck effect. But these are both examples of genetic drift. And they both start with a large population, but you'll see that something happens to cause the population to become smaller. So we're looking at a population of ladybugs here, and this is for the founder effect. This is when we have a few individuals from a population start a new population. So we have some founders that are going to leave the original population, and they're going to found or start a new population. But the thing is, these ones that leave to start the new population have a different allele frequency. So what happens is, instead of having an equal distribution in our original population here, we have approximately half and half red ladybugs with the yellow ladybugs. If let's say a pregnant red ladybug happens to be separated from the main population and then lays her eggs on an island, because she's the only one there, it's quite possible that now we can have an island that is entirely populated by only red ladybugs. The yellow is essentially lost from this population. It's gone. And if they continue to, without any more immigration, we would never see the yellow ladybugs on this island. The fortunate thing in this particular example is that if we want to add some genetic variety to this island, and we want to make this population have it stronger, we could always bring over a yellow ladybug and add to the genetic variety and make it stronger. But that just doesn't always happen in nature, so if we wanted to make it happen, we could. But the nice thing, and the reason why I point that out here, is that we haven't really lost the genetic variety. The genetic variety is gone from the island, from the new population, but the original population still has its genetic variety. It still has the yellow gene, definitely part of the population. That remains relatively unchanged. So in the founder effect, we see a new population with a different gene frequency, just because of the founder who started that population. We haven't really truly lost the alleles because they're still available in the original population. The scarier scenario is the bottleneck effect. The bottleneck effect is when we have a really large population to begin with, but then something happens to the population and we see this drastic reduction in population. And this is where the ideas of, if we have an endangered species. We don't have that many individuals left. We don't have a whole lot of genetic variety left. So if we look at our original parent population here, you can see I'd say maybe it's half and half, blue and yellow alleles. However, maybe the yellow alleles even dominate a little bit more. But once that population gets cut down, we can see that there's mostly blue alleles in that. As they begin to survive and eventually reproduce, we begin to see that the blue allele becomes more and more common. So, at least in this particular scenario, we haven't lost the yellow allele completely, but the allele frequency has shifted very suddenly just because of this chance event where the bulk of the population has disappeared. It's been slaughtered, outfished, overhunted, succumbed to a new environmental pressure, a new virus, whatever it may be, and we're left with just a handful of individuals left. By the way, this is what happens to give us antibiotic resistance in bacteria. Because we kill off most of the bacteria, but we leave the resistant ones, and they stay behind, and grow until we have a whole new population of now resistant bacteria. Not a good scenario for us as humans. Now, to actually think about this in terms of living organisms, we have the spore population over here. As you can see, there's a decent distribution of the dominant allele and the recessive allele in the gene pool. It looks to be about half and half based on the genotypes that are given. If, for some reason, this population is dwindles down to just these two boars, notice their genotypes. We've completely lost the capital B allele. Now, because this is the bottleneck effect, that would mean that these originals up here are all gone. We're only left with, the two little b organisms. So we've lost the capital B allele. There is no original population to go back to. They've all passed away. So we can't move forward from here. This gene, this allele, the capital B in this example, is now lost forever. And that's one of the problems with the bottleneck effect compared to the founder effect, is that the bottleneck effect doesn't allow us to retrieve the allele sometimes. Alleles can be lost forever when we do this, which is one of the problems when dealing with endangered species. If those alleles are lost forever, we can never make the population as genetically strong as it once was.